Hello everyone, I am Rafayel. I am from YerevaNN. I am here to present our paper which was accepted to ICML workshop this year. Before jumping to the main topic, I want to talk about swans. It is said that in old times people believed that all swans are white, and even black swan was a metaphor for events that has zero probability. But the story changed 400 years ago. Someone from Europe saw black swan, and of course it was in Australia. After this, the black swan was a metaphor for events that are rare and have high impact. So when you show only white swans to people, they believe that all swans are white, and it is similar with machine learning models, and it is because of the same domain assumption in traditional ML. In machine learning, we expect that our training set and testing set are coming from the same domain, but in reality, we may have a case when data from another domain comes for testing. And in these cases, our model struggles to give accurate results. Here is one example. This example is called cow-camel example. Here we want to classify cows and camels. And in training set, our cows are on the grass and camels are in a sandy environment. And because of this, after training, when we want to do prediction, if we give an image of camel on grass, it will say that it is cow. It is because of spurious features in input. Here the spurious feature is background. For the model, it is easy to learn background because of its color than complex features of the animal. Another example is water birds. This is a popular benchmark dataset for the subpopulation shift problems. Actually, we also use this dataset for our experiments. Here we want to train classifier for water birds and land birds. And the birds are seen in two environments, water environments and land environments. Here we have 4 groups, and both in training and testing sets, we have examples from these 4 groups. But our testing set is balanced in the sense that, for example, for water birds, the images of the images with water background and land background have equal amount. But the training set has imbalance. You can see that water birds in land and land birds in water have low numbers. And because of this, our models here also relies on spurious correlations. And in this case, it is the background too. So our problem setting is the following. We are interested in this subpopulation shift problem. We use water birds dataset, and we use frozen pre-trained representations and train only the linear layer on top of that. And the goal is to maximize the worst group accuracy. Before talking about our paper, I wanted to talk about a paper from MedAI. They also used frozen pre-trained networks. They did lots of experiments with different neural networks, and they were pre-trained with different sizes of datasets. This paper shows that there are models that have good representations. You can see that the gap between average accuracy and worst group accuracy is low for some models, and it is interesting to understand what properties do the representations of different neural networks have. And for this, we thought that one of the most important property can be axis alignment. We say that the representation is axis aligned if each neuron of the representation corresponds to one feature from the input. For example, if Z2 corresponds to the wing of the bird. And if the representations are not fully axis aligned, and probably they are not fully axis aligned, it is interesting to understand does there exist a linear transformation that would map that encoding to a new encoding which is axis aligned. To answer these questions, we tried different experiments, and we wrote this paper. Before talking about the experiments of the paper, I want to talk about two tools that we have used. One is CAPTUM. We use integrated gradient algorithm from CAPTUM. If you don't know what this is, don't worry. It is just something that can take the image and the feature extractor, and for each neuron of the encoding, it will say which part of the image it looks. For example, in this case, CAPTUM says that Z1 looks at that white pixels in the input. The next, we use DATIC for segmentation. We segment the bird pixels of the image. And here is one of the most interesting parts of our paper. We do identifying spurious features, and for that we do the following. We segment the bird pixels using DATIC. We calculate attribution scores for the image, and after that we calculate the mean attribution, the mean of the attribution scores of bird pixels for the entire data set, and we do the same with background pixels, and we rank the neurons ZY according to the attributions of foreground minus background, and we keep only top K neurons. By this way, we hope to keep only the neurons that look at the bird. The next thing that we did was designing this autoencoder, which we call group-wise autoencoder. This autoencoder has 3 encoders. You can see that we have ZY, Z, and ZC encodings. ZY is responsible for keeping the information of the label. And for that, we train linear classifier on top of that. We do the same with background label, that is ZC. And we have ZN for reconstruction. We want to do reconstruction because we don't want to lose information. We just want to disentangle spurious and core features. And we also have mutual information minimization part for Z, Y, and ZC. So this autoencoder has allows with 4 components. One is for label prediction, one is for background prediction, one is for reconstruction, and one is for minimizing mutual information. Here is the table of our experiments. Here is the table for ResNet 50. This first line is for the standard training, and we see that we have huge gap between average accuracy and worst group accuracy. We computed upper bound for this to understand what is the highest value that we can aim to reach. And for this, we do cross-validation on test set, which is a balanced set. Then one of the most interesting part is the experiment with Captum, which I described. We do Captum and we keep only 100 features from 2048 features. And we see that we have improved worst group accuracy and also average accuracy. This is interesting because we remove more than 90% from the representation and we have good results. Then we rotated the encoding. By rotating, we don't lose information, we just mix the neurons. And we see that the performance dropped and it is worse than the standard training on Z, which means that original Z was somewhat axis-aligned. The next thing was autoencoder, and we see that when we train linear layer on top of this ZY part of autoencoder, we have better results. We try to calculate upper bound for the representation of autoencoder to see if we lose information, and we see that we don't lose much information here. Then we tried to combine Captum and autoencoder. We tried two experiments. One with is Captum applied on ZY of autoencoder, and the other one is Captum applied to the concatenation of three parts of the autoencoder. And we see that the results are the same, and this is because the Captum chose the same 20 neurons. Actually, the 20 neurons are from ZY in both cases. And the results are better than Captum results or autoencoder results. We discovered that applying PCA helps to get better results. You can see that applying PCA on autoencoder has the highest result. The intuition behind this is that when we train autoencoder, we would still have spurious features inside ZY, but that features have low values, and because of that, the variance of core features are high. So when we do PCA, we probably remove the spurious features and get better results. We tried to do PCA with all the components, 2048 in this case, and the results are the same with just with autoencoder. We tried to do PCA with original Z, and the results are worse because it probably loses much information, much useful information. We have similar tables for RegNet and Dino version 2 representations. They are very similar. The only thing that I want to mention is that when we apply Captum to Dino representations, we don't get good results. But when we apply Captum to the representations of Dino plus autoencoder, we still have good results, which means that the Dino encodings are not axis-aligned probably. To conclude, our key findings are the following. By removing features that mostly look to the background, improves our worst group accuracy. We saw that pre-trained representations are relatively axis-aligned. We found a way to train autoencoder so that we have ZY that has mostly good features, and by applying PCA on top of ZY, we get better results. So that's all.
The alternative way to suppress spurious features is to apply variational inference with very aggressive tool regularization. Did you try this?
No, we don't try experiment with variational inference.
So this technique is so popular in speaker verification task. And you can apply variational inference for classification task with regularization and suppress spurious features.
Yeah, we can try. Thank you.
So it's similar to VAE? Or it's different?
No, just predict logits like means and sigma and apply divergence to make representation like mixture of Gaussians.
Presentation of mixture of Gaussians. I want to understand where does the signal from spurious come from? It's like in this setting, you had labels, right? So you know that this bird was on water background and this bird was on land background. In the setting that you described, did you meet this label?
Now you just obtain the sparse representation, and after that you can analyze it and find what specific coordinate correlate with some class.
So for every speech you get a sparse representation and you hope that it does not contain spurious stuff?
Yes, if you have the right configuration of hyperparameters.
So what are the results without this reconstruction part? Do you remember numbers?
They are similar, 2% better than with reconstruction.
Have you planned or have you studied the unsupervised frameworks like SimCLR, SimCLR, or like do you find some similarities, or are they better, or do you plan to do that?
As I understand the question, you suggest to do some augmentation, right?
No. In the SimCLR CLR framework, they suggest to learn representations in unsupervised fashion, and then they fine-tune on the dataset. Like in this way, you can also study what representations in this framework are learned, and it is really interesting to understand are there like key differences or.
I see. We didn't try to study the representations of that networks. We don't want to train the networks because we want to train linear classifier on top of frozen representations. But I think it would be interesting to do experiments with that representations pre-trained on other datasets.
I can follow up on that. So SimCLR requires negative sampling to do the training, and then there was this BYOL about which yesterday Rafayel was talking. That kind of eliminated the need for negative samples, and Dino version 2 is actually using BYOL ideas on video transformers. So you can assume that this Dino version 2 results are like the next generation of SimCLR, but it doesn't mean that your question is not valid, because between RegNet and Dino version 2 there was a lot of progress, including SimCLR. So for example, we don't know where does this axis alignment disappear. Like in RegNet you have axis alignment, and Kaptum helps, which means that there are some features that if you remove it will be better. But in Dino it's not there, so we don't know whether it happened in SimCLR or in BioL or in Dino.
Let's think Rafayel again.
Thank you.